Welcome. So in this video we will learn all about the refractive index of milk. Now, as we know that when light passes from one medium to another, bending of light happens, and this bending of light is nothing but the refraction. So if you see that I is the angle of incidence, what is the angle of incidence? The angle at which the incident light makes with the normal is known as angle of incidence, and angle of refraction is the refractive light. That angle which the refractive light make with the normal, that is known as angle of refraction. So we know that when a light passes from one medium to another, it gets refracted, and the angle at which it is refracted is known as angle of refraction. And if you want to define refractive index, it is defined in the ratio of the velocity of light in air to the velocity of light in medium, that is c by v. And another we can define it in another way, that is defined as the sin I by sin r, that is sine of the angle of incidence to the sine of angle of refraction. So refractive index of transparent medium is defined as the ratio of velocity of light in air to the velocity of light in the medium. When a ray of light passes at an angle through the interface between two transparent media of different densities, an abrupt change in direction, that is bending of light, happens, and this phenomenon is known as refraction, bending of light. Now, refractive index is given by also defined as sin I by sin r. This is also known as Snell's law, when where I and r are the angles between the incident ray and the refracted ray of light, respectively perpendicular to the surface of the substance. Now, if we also know that if the light travels from a less medium to a denser medium, then refracted light will be near to the normal. This refracted light will be near to the normal. Now, when light travels from a denser medium to a less dense medium, so here we can see that light will be away from the normal. So the refracted light will be away from the normal. That is mean to say, when the ray of light passes from a less dense to a more dense medium, the bending is towards the normal to the interface. So here bending is towards the normal to the interface, while when the densities are reversed, that is if the light passes from a denser medium to a less dense medium, then bending happens away from the normal, as shown in this figure. So here bending away from the normal, here bending is towards the normal to the interface. Towards the normal, here it is away from the normal. Now it is very important to note that refractive index varies with the temperature and the wavelength of light. So whenever it is mentioned for any liquid or any substance, refractive index is given, we have to mention the temperature and also the wavelength of light which is used. Now, at a constant temperature and wavelength, the refractive index is a characteristic constant for a particular pure medium and can be used to determine the purity of a substance and to determine the composition of mixtures of known constituents. So we can determine the purity also, so we will see in the coming slides, and also the composition of the mixtures of known constituents, that also can be determined, that this part we will cover in the coming video. Now, coming slides. So refractive index values are usually measured using a light of constant value. Generally we use a D line of the sodium spectrum, that is at 589.3 nanometer. D line of sodium spectrum is generally used, and generally it is taken at 20 degrees Celsius. So always we have to mention that the wavelength of light that has been used and also the temperature. So generally we are writing in this way, and this is sodium wavelength here D, and then temperature here is D 20 degrees Celsius. We are measuring at 20 degrees Celsius. So D line of spectrum, that is the 589. So here N 589 20. This way also we can write. Now, coming to the refractive index of milk. So first point is that refractive index of milk is difficult to estimate. Why? Because there are calcium and fat globules in milk which scatter the light. So the refractive index of milk is difficult to estimate, but it is possible to make accurate measurement of refractive index of milk using a refractometer, in which a thin layer of sample is used, like every immersion refractometer is there. So these we will cover in the coming slide. So if we can use a thin layer of sample in this type of refractometer, then we can accurately measure the refractive index of milk. Now if we compare the refractive index of water with that of the milk at 20 degrees Celsius, refractive index of water is 1.3330, and refractive index of milk at 20 degrees Celsius using the D line of sodium spectrum, that is 589 nanometer, is normally in the range of 1.3440 to 1.3485. Okay, so these differences are there. So refractive index of milk is higher as compared to the water, that is solvent. That solution is having a higher refractive index as compared to the water. Now why this is higher? Because of the presence of components of milk. Now the difference between the values of refractive index for water and milk reflects the presence of dissolved substances. These are the dissolved substances which contribute to the refractive index of milk, such as casein, whey proteins, lactose and minerals. So here we can see that larger colloidal substances such as fat globules and air bubbles do not contribute to the refractive index of milk, as the refraction happens between the interface of the continuous medium and air. So fat globules and air bubbles do not contribute to the refractive index of milk. Now coming to the components or factors which affect the refractive index of milk. What are the components or factors which affect the refractive index of milk? That we will see in this slide. Now increase in refractive index of a solution over that of pure solvent is directly proportional to the volume concentration of the solute. We have seen that in milk there are many components are there, so there happen increase in the refractive index of milk over water, and this increase in refractive index of solution over pure solvent is directly proportional to the volume concentration of the solute. That's what is meant by volume concentration, is the product of solution density and the solute concentration, that is rho CV, rho CW. Now a specific reflexive increment can be defined as, this is R denoted by R, that is specific refraction increment, that is the refractive index of solution minus the refractive index of the solvent divided by here volume concentration, that is sigma CW. So it can be written as delta N divided by rho CW. So if we rearrange it, delta N will be equal to here if we write delta N is equal to R rho CW. So here delta N can be, if we go here, then it will be rho R rho CW. Now it can be again written as delta N is equal to rho summation MR. So CW, we can write CW as MR, that is mass of the component, each component, and the R is the specific refraction increment. So increase in the refractive index, or we can say that refractive index increment for a multiple component system is given by N solution minus N solvent, that is equal to the density and summation of MR, that is mass of each component, into its specific refraction increment. And if we summation, because it is a additive property, so increase in refractive index or refractive index increment can be calculated, where mass M is the mass fraction of a solute, R is the specific rotation increment, and rho is the density of the solution. Now if we see that it has been reported that casein is show the specific refractive increment of 0.207 ml per gram, soluble proteins show 0.187 ml per gram, and lactose shows 0.140 ml per gram. Obviously fat is not contributing to the refractive index, as the refraction happens between the interface of the air and the continuous medium. Now if we see the total contribution of the refractive to the refractive index of milk containing, say we consider 2.3% casein complex, 0.83% serum proteins, and 4.83% lactose in milk, then the refractive index of milk becomes, so thus here the specific refractive increments, if you see by them, will be 0.00500 plus 0.00159 plus 0.00695, that will total equal to 0.01354 to the, so this is the contribution to the specific refractive increment in ml per gram. Okay, now remaining residues, which include the minerals, vitamins, and some organic acids, they contribute to 0.00166 to the total difference between the refractive index of water and that of the milk. So as already told, fat do not contribute to the refractive index of whole milk because refraction occurs at the interface of air and the continuous phase. Now refractive index measurements can be used satisfactorily to estimate the SNF content of milk and condensed milk. That is, so if we are increasing the SNF content, the refractive index increases, and that is, they are generally linear, and by establishing the correlation between the two, we can determine the SNF content of the milk and the condensed milk. Generally, there is a linear relationship between the solid content and refractive index, but this relation varies with loads of milk because the composition varies among the milk. So this the lactose, especially the lactose and protein ratio, varies among the milk. So therefore, it becomes a little difficult to or the refractive index of milk with accuracy cannot be determined. Now here it is written that sterilization and storage do not alter the refractive index because we are sterilizing because it is because of the soluble components which are present in milk, and most of the time we are filtering to remove the fat and also proteins. The sterilization of milk is not affected by this. Does not affect the refractive index of milk. Also storage also, that if you are properly storing the milk, then the refractive index is not affected that much. Now there is a term which is known as specific refractive index. So specific refractive index is given by this formula written on the slide, that n square minus 1 divided by n square plus 2 into 1 by sigma in the specific refractive index. And as you told, that the relation between the refractive index and total solute varies with change in the concentration and composition of solutes in the milk, especially lactose proteins. So, but there are attempts have been made to measure the total contribution of the solids and casein in milk and milk products by estimating the refractive index. Now, if we see the milk has a specific refractive index ratio 0.2075, the specific refractive index K is calculated from this formula, and the milk has a specific refractive index of 0.2075. Just to tell you that this, and the product of refractive index and the density is constant. Here that is known as the specific refractive index. Now let us see how to determine the refractive index of milk. So there are two types of refractometer. One is known as immersion refractometer, other is known as the Abbey refractometer, that we will see in the next slide. That immersion refractometer, why it is called so, because initially we are immersing the refractometer. These were mostly the handheld refractometer, and simply we have to immerse them in the milk or in any liquid, and then we are making note of the reading, that is between the dark scale and the white scale. So here blue shade is there and the white shade is there, so the boundary between the two is taken at the reading of the sample. So that is how much this boundary indicates that how much light has been refracted by the sample. So it is used to measure the refractive index of milk, and if you especially you want to remove the interference from the proteins and fat, then what milk serum is prepared by treating the milk with copper sulfate and to precipitate the proteins. And alternatively, we can also use 10% TCA to precipitate all the proteins in milk, and then proteins are removed by filtration. A drop or two is placed on the prism of refractive, and the refractive index is measured. Okay, so just to remove the hindering components, that is fat glues and proteins from the milk, and especially if you determine the contribution by the lactose or the sucrose in sweetened condensed milk, then you go for in this way. Otherwise, we can take directly milk also, but that proper calibration should be there. Okay, so this is immersion refractometer. But in the white, these are called immersion. We can take a drop of milk also in this prism. So either the drop is immersed in the prism or the prism is immersed in the drop. Either way, that means to say the whole prism has to be covered with a liquid whose refractive index is being measured. Now there is another refractometer which is Abbey refractometer. So how it differ from the immersion refractometer? That Abbey refractometer refractometer is a modified version of the refractometer. It is provided with a narrow rays for measuring the RI for fats and oils. So specifically it is designed for measuring the RI of fats and oils which are having narrower range of the refractive index. So in this we have a arrangement for circulation of water, so that fat remains in melted state, because we are reading of liquid at mostly taken at a temperature at which they are in uniform in state. So to maintain ensure that fat remains in the melted state, we have a arrangement for circulation of water, and the temperatures can also be controlled in this case. So in a way refractometer we have a temperature control mechanism is there. It can either be using water, that is we are circulating the water, or we can use the ATC, that is automatic temperature compensations are there, that in some of the digital barometer automatic temperature compensation are there to maintain the temperature at which we want to take the reading. Now scale is usually graduated in number, that is 43 correspond to 1.4545, that is this is known as Barrow refractometer reading, and this is the refractive index. So these are simply the two different scale. PR reading can be converted to refractive index and vice versa. So a refractometer is used to measure the purity of ghee. Mostly it is used to measure the purity of ghee. A drop or two of ghee droplets are placed on the surface of a refractometer prism, which is heated at 40 degrees Celsius through water circulation. Now PR reading and refractive index are interconvertible, and we see that FSA has given standard of PR reading of ghee of 40 to 44. Higher values indicate the adulteration, or any deviation from this indicate the adulteration from the animal body fat or vegetable oils. Please note that when concentration of vegetables are added to the ghee, or any body fat added to the ghee, the PR reading of ghee increases, and that may indicate the presence of some adulterant in ghee. Now refractometer, you said there are two refractometers, so this is also a refractometer, and here if you see this is also the digital type of refractometer available here. So we are placing a drop of the sample oil here on this prism and then taking the reading. So here in this we are making use of ATC, that is automatic temperature compensation devices are there, which maintain the temperature of the liquid at particular temperature. Say because of ghee, we know that PR reading of ghee always taken, but reading ghee is always taken at 40 degrees Celsius, so that temperature can be maintained using ATC, in this case digital refractometer, and through water circulation in case of a refractometer. So why to measure the refractive index? Again we have covered it. Just to repeat that we can determine the total solid content of the milk and the condensed milk quickly and accurately. We can determine the total solid, and the sugar content is really in condensed milk or sweetened condensed milk. If you want to measure the sucrose content, that also can be done. And purity of ghee, I have told you that FSA has given standard for it, that 40 to 44 should be there for ghee, and any deviations indicate the adulteration. So PR reading is used to assess the purity of ghee. Pure ghee has a standard PR value, and deviation can indicate the adulteration. Also we can determine adulteration if water is added to the milk. Obviously the TS will decrease, that and if TS is decreasing, that is related to the refractive index. Obviously it indicates the presence of water. So you can refer these books to understand more about the concept. Thank you.